So welcome to this presentation on the acid dissociation constant. So you might remember your Year 12 studies where we made this distinction between a strong and a weak acid. We said then that the strong acids were acids that would completely dissociate their H+ ions. So things like hydrochloric acid, every single one of those hydrogens in that molecule would separate from the chloride ions and go into solution. A weak acid is where not all of the hydrogens would do this. And in fact, this partial dissociation would go both ways, with some coming into solution and some moving out. It was a relationship which we gave the equilibrium symbol for because there were ions coming in and out of solution. Now, the dissociation constant, K subscript A, gives a mathematical number to how much an acid will undergo hydrogen dissociation. For us to understand what this acid dissociation constant really means and how we can use it, we should compare it to the equilibrium constant Kc. Now, as a reminder, what Kc was, if we had any kind of reversible chemical reaction, where a certain amount of chemical A was added to a certain amount of chemical B, where those amounts are given by lowercase a and b, and it would turn into some products, a certain amount of C and a certain amount of D, but not really products because the reaction can go the other way as well. So basically these chemicals can turn into those chemicals and back again. It is a reversible reaction. Now, we can define an equilibrium constant which tells us about the favoured direction of this reaction. Is it to the right, producing those products, or is it to the left, producing those reactants? And the way that we do it is we take the concentration of each of the chemical, we find the product of those concentrations to the power of their quantity, so like how many moles, for example, of each are present. And what you can see is we have this, we have on the numerator line we have the products, and on the denominator line we have the reactants, or equivalently the things on the left and the things on the right. And so what we get is some situations where the numerator wins. When the numerator wins, we're dividing a big number by a small number, and we basically are going to get a number that is bigger than 1. And in that case, there is the reaction goes to the right, and we have the favoured formation of the products, those things on the right, C and D. But if it is less than 1, then the denominator wins. You're dividing by a big number. It's going to make Kc much smaller than 1, meaning that the reaction is going to be going more favourably to the left, producing more reactants. If it is exactly at 1, it means that it is going in both directions equally, in a lovely little equilibrium there. Now, we use this to determine whether or not this reaction is favourably going to the right or to the left, and we're going to use very similar things for the acid dissociation constant. The equation for a weak acid would look like this. It would have a single acid on the left-hand side, the equilibrium symbol, and then the H+ ions, and the rest of the molecule that they have detached from. That molecule is now an ion. It has lost its positive charge. It is now itself negative charged. Now, we've drawn this as an equilibrium, which means that we can apply an equilibrium constant to this and see whether or not this is more favourably going to the right or to the left, and find out some interesting information about it. So if the numerator was the products, those things on the right-hand side, the concentration of the H+ ions multiplied by the concentration of the A-, where A is the rest of the molecule, whatever it be. Now, both of these, it's a 1 mole to 1 mole, so both of these are to the power of 1. So we don't have to worry about that. Now, there's only one reactant, and so that goes on the denominator line, the acid itself, the concentration of the acid. Now, that ratio equals the dissociation constant, and its units, well, it would be the units of concentration times concentration divided by concentration, which means you'd have a cancelling out of 1 moles per decimeter to the -3 on the top and at the bottom, leaving just that the units for Ka would be moles per decimeter cubed. A good example of a weak acid is ethanoic acid, or vinegar, to me and you. Now, what we have in vinegar, we have a CH3 group connected to a C, double bond O, and an OH. Now, the final H in that OH group, or that COOH group, will dissociate first, and so we're looking at that dissociation. So on the top row, we would define that the concentration of the H plus ions multiplied by the concentration of the CH3COO minus ions, that would be on the top line, divided by the concentration of the acid before we considered dissociation, how much acid was physically in that space, how many moles were in 1 cubic decimeter. So it's totally temperature dependent. We normally take it to mean 25 degrees C. If the numerator is larger, then we get a higher value of Ka. It means more dissociation for the concentration that we originally have been given. If the top was small, not many ions have gone into solution compared to how many molecules there are, then Ka would be significantly smaller and it would be a weaker acid. With strong acids, the value of the acid dissociation constant goes to infinity. Because if you think from the previous slide, on the numerator we would have basically the number of H plus ions multiplied by the number of molecules, which would literally be all of them multiplied by all of them. And so it goes off to infinity. But for a weak acid, we actually get a value somewhere between the range of 10 to the minus 3 and 10 to the minus 7. Now, the largest of all of these, phosphoric acid, the one that dissociates the most, is 7.2 times 10 to the minus 3. Whereas the one that dissociates the least on this list is carbonic acid, 4.3 times 10 to the minus 7. Now, it's important to note that those things that are like sulfuric acid or carbonic acid, we're going to give a Ka value for a first dissociation, knowing that removing a second H plus ion is obviously much more difficult. The molecule physically changes so that it's more reluctant to do so. So we always quote the first dissociation in these values. Now, the range in these values here between minus 3 and minus 7 is 10,000. So whenever we have differences in numbers like this, it makes sense to introduce a logarithmic scale. In the same way that we calculate the powers of hydrogen, the pH of an acid, by taking it equal to the negative log to the base 10 of the concentration of the H plus ions, well, what we can also do here is we can do the same with this value. If we took the powers of the acid dissociation constant, or pKa, it would equal negative log to the base 10 of the acid dissociation constant Ka. And of course, we can find Ka by rearranging that. It is equal to 10 to the power of minus pKa. And what this indicates to us is how strong the acid is, because a lower pKa indicates a stronger acid. It essentially flips this upside down. Small pKa comes from large Ka values, as we shall see. So a lower pKa means more dissociation of H plus into solution, and a higher pKa indicates a weaker acid with less dissociation into solution. We can compare them on a really straightforward scale with very similar looking numbers. And we're going to use this later in the next chapter to look at buffer calculations. But here are some values here. So hydrochloric acid with its infinitely large Ka is also going to have a negatively infinitely large pKa. So we'll forget about that one for now. But something like acetic acid, 1.8 times 10 to the minus 5 is its Ka, has powers of Ka equal to 4.74. It means that these acids have a value of pKa fairly similar to each other. And even water, which is essentially neutral, it still has some OH minuses and H pluses floating around. And so we could describe it as a very, very weak acid indeed, with a pKa equal to 14. So the bottom rule is, the bottom line, that in a strong acid you have a large Ka and a small pKa, and in a weak acid you have a small Ka and a large pKa. Now I think we should talk about wine, because wine contains 3 types of weak acid, and it's interesting to see how they work. So the first in sweet wines is this acid called sulfurous acid, H2SO3, and it derives from the sulfur dioxide gas, which is frequently put above the liquid when the bottle is corked. Now this is, sulfur dioxide, quite toxic to microorganisms, and it stops microorganisms eating the sugars in your sugary wine. It's sometimes why it can smell of eggs when you first pop a cork, but quite often it is immediately sent out by the carbon dioxide, which is dissolved in the wine, which then basically forces that sulfur dioxide away. However, some of it ends up in solution, the sulfurous acid that we see there. It's dibasic with 2 hydrogens to donate. One of them, it dissociates far easier than the other. So one of them dissociates with a pKa of 1.92 and the other one with a pKa of 7.18. And you can see that ultimately what is produced by the second dissociation there is SO3 sulfite, which alongside dehydration is one of the major causes of a hangover. So if you find that sweet wines, champagnes, go to your head and leave you with a headache, then maybe try something less sweet, because you're far less likely to have one of these products of double dissociation. 2 more acids found in wine. Malic acid contributes to that sharp green and crisp taste, making it refreshing. And then there's tartaric acid, which stabilizes the pH in the wine, crucial for the wine's stability and longevity. Now look at these. Malic acid and tartaric acids are like mutant versions of alcohol, which of course just have a single OH group. These OH groups connected all over the place. Now the hydrogen that dissociates first is the one in the COOH group. So on the far right and the far left of this molecule, and it doesn't matter which one as such, but once one has gone, the second one is much harder to dissociate. It means that there is a sequence in which these hydrogens will be stripped off from their acid. And you can see that for this, the pKa of the COOH group is 3.4, and for the one on the far left, it's 5.2. So one will dissociate readily, and the other one would only dissociate in a much smaller quantity. And whilst we're here, we might as well talk about citric acid found in lemons and limes. So this is tribasic. There's 3 hydrogens that could come off. There's 3 COOH groups. It means there would be 3 dissociation constants. The first one to be removed, the second one, and the third one. And it becomes progressively harder to remove a proton as what remains becomes more and more negatively charged. So here we would need to calculate all 3, and we don't yet have the machinery to do that. But just so that you know, citric acid, tribasic, 3 different values of the acid dissociation constant.